Welcome to the Deep Dive. You're joining us today because, well, you want to get smart, fast, on what's next in mobile tech.
And that's exactly what we aim to deliver.
Yeah, today we're looking beyond just, incremental updates. We're talking about a really fundamental shift with 6G.
And the key to unlocking all that potential, it seems to be artificial intelligence.
Exactly. AI.
That's right. So we're diving deep into how AI is really poised to revolutionize network slicing.
Which is a technology already in 5G, right?
It is, yeah, but it's about to become exponentially more powerful, more dynamic in 6G, all thanks to intelligent automation.
And our guide for this, our roadmap, is this fascinating research paper you shared, Redefining 6G Network Slicing, AI-driven Solutions for Future Use Cases, published just this past January. So think of this deep dive as your shortcut, really, to understanding how AI is going to be the mastermind behind the scenes of future mobile networks.
And our mission today, it's pretty straightforward. Understand how this AI-driven network slicing can actually meet the really demanding requirements of these next-gen 6G applications.
Okay, so what are those requirements? What capabilities is 6G aiming for that make this AI approach so critical?
Right. Let's jump in there. We know 5G brought us, eMBB for speed, URLC for reliability, and low latency, MMTC for lots of devices.
The basics.
Yeah. Now, 6G takes those core ideas and just pushes them to the absolute limit.
Okay.
And it also introduces entirely new service types with even, tougher specs.
Can you give us some examples? Like, what are these next-level services?
Okay, take further enhanced mobile broadband, or FMMB. We're not talking just slightly better streaming here.
Right.
We're envisioning downlink speeds hitting, like, a terabit per second, maybe even more.
A terabit, wow.
Yeah, imagine truly seamless, immersive 3D video, totally realistic VR and AR, the kind of stuff that could genuinely transform how we work, how we play.
That's a huge leap. What about those mission-critical applications, reliability, latency?
Right. For those, 6G introduces extremely reliable and low latency communications, ERLLC.
ERLLC. Okay.
This goes way beyond 5G's URLLC. We're targeting reliability of, like, 1 failure in a billion transmissions.
1 in a billion.
Yeah. And latency down in the tens to hundreds of microseconds.
Microseconds. That's almost instantaneous.
Practically. Think about telemedicine, remote surgery, critical industrial automation, any scenario where even a tiny delay or a drop packet could be, catastrophic.
Actually, critical reliability then, and the scale, connecting devices.
Yeah. That's where ultra-massive machine-type communications, MTC, comes in.
Okay.
6G is aiming to support a connection density of maybe 10 million devices per square kilometer.
10 million? That's 10 times 5G, isn't it?
Exactly. 10 times. This is fundamental for realizing, the full vision of smart cities or truly pervasive IoT.
We're talking potentially trillions of connected devices then, not just billions.
It scales incredibly. And then you've got services that actually blend these extreme requirements.
Okay, like what?
Well, massive, ultra-reliable, low-latency communications, or MURLLC.
MURLLC, so that combines.
It combines the high density of MTC with the low latency and the extreme reliability of ERLLC.
What's an example use case there?
Imagine millions of remote health monitoring devices, maybe wearables, all operating simultaneously with that mission-critical reliability and responsiveness.
That paints a picture of just incredible complexity for the network to handle.
It really does. And finally, there's one more category, mobile broadband reliable low-latency communications, MBRLLC.
Okay, MBRLLC. What does that mix?
This one merges the high data rates, like FMMB,
Yeah.
with the ultra-low latency of ERLLC.
High speed and near-instant response. What needs that?
Oh, things like autonomous vehicles are a prime example. Delivery drones, too.
Yeah.
And vehicle-to-everything, V2X communication.
Right, where you need both massive data transfer for sensors and maps, but also immediate reaction times for safety.
Precisely. Both are non-negotiable there.
Okay, so it's crystal clear now. 6G isn't just a speed bump. It's a fundamental reimagining of what mobile networks can do. Reliability and latency are just paramount.
Absolutely.
So why can't our current 5G networks handle this? What's the actual bottleneck?
Well, a core challenge is that 5G, while it was a huge step forward, it just wasn't designed to consistently deliver that level of extreme reliability and ultra-low latency across so many different demanding applications all at the same time. The architecture, the resource management techniques in 5G, they aren't built for that level of, let's say, dynamic and super stringent control needed for 6G scenarios.
Okay, and this is where network slicing really comes into play, right? The paper calls it a key enabler.
Exactly.
So remind us again, what exactly is network slicing and how does 6G elevate it?
Right. So think of network slicing as taking the single shared physical network infrastructure.
Yeah, the towers, the fiber.
Exactly. All that physical stuff.
Yeah.
And dividing it into multiple virtual independent networks. We call these slices.
Okay.
And each slice is custom built. It's optimized for the specific needs of a particular application or service type.
So instead of one size fits all,
Right.
you get a bespoke network slice for, say, that autonomous car needing near zero latency, and maybe a totally different slice for streaming 8K video that just needs tons of bandwidth.
Precisely that. And what's really transformative about 6G slicing is the ambition for truly dynamic resource allocation.
Dynamic meaning.
Meaning the network intelligently adjusts things like latency targets, bandwidth allocation, even security parameters, almost in real time.
Wow.
Perfectly tailored to the constantly changing demands of the traffic flowing through each specific slice.
You mentioned security there. How does slicing actually help make things more secure?
Well, because each slice is essentially a logically isolated virtual network.
Uh-huh.
Any sensitive data that's transmitted within that slice is kind of contained. It stays within its dedicated environment.
So it limits the blast radius if something goes wrong.
Exactly.
Okay.
It significantly limits the potential for breaches or unauthorized access compared to a traditional monolithic network where everything's mixed together.
Got it.
Yeah.
Now, we often hear terms like NFV and SDN network function virtualization and software-defined networking when talking about network evolution. How do they fit in? How do they actually enable this slicing in 6G?
Yeah, they're fundamental building blocks.
Yeah.
So NFV lets network functions that used to be tied to specific expensive hardware.
Like firewalls, routers.
Exactly. Things like firewalls, load balancers, routing protocols. NFV lets them run as software on standard off-the-shelf servers.
Okay, more flexible.
Much more flexible. It provides the agility and scalability you absolutely need to rapidly deploy and manage all these different virtual network slices.
And SDN.
SDN, software-defined networking, complements NFV. It provides a centralized control system, like a brain, that can manage and configure the underlying network infrastructure.
So it tells the NFV software what to do.
Kind of, yeah. It allows for that dynamic reconfiguration of slices based on real-time needs and those service requirements we talked about. It makes the whole idea of adaptable on-demand slicing actually feasible.
Okay, so NFV and SDN give us the tools to create and manage the slices. But AI, that's the game changer, right? How does AI come in and make this even more powerful for 6G? What's the AI magic?
Right, here's where the real leap happens. AI introduces a level of intelligence and, crucially, automation that traditional network management just can't match. It lets the network move beyond just reacting to current conditions. It starts predicting future resource needs.
Predicting. How?
By analyzing traffic patterns, looking at the demands of different applications over time, learning historical trends, it allows for real-time prediction.
Oh, okay.
And this predictive capability leads to far more efficient allocation and, importantly, utilization of network resources. Less waste, better performance.
So instead of just setting fixed rules for each slice,
Which is kind of how 5G slicing often works.
AI can learn and anticipate what's actually needed, almost like an expert traffic conductor who knows rush hour is coming.
Yeah, that's a great analogy, yeah. The research really highlights this shift away from that static rule-based slicing towards intelligent, adaptive, and automated management, all driven by AI. And that includes the really crucial ability to proactively allocate resources based on learned patterns.
So give me an example.
Okay, think about it. If the AI knows that, say, video streaming traffic always spikes in a certain residential area around 8 p.m.,
Right.
it can pre-allocate more bandwidth to the video streaming slices in that area before 8 p.m. hits.
So it smooths things out, minimizes latency, buffering.
Exactly. Ensures a smooth user experience proactively, not reactive.
That sounds incredibly dynamic. Now, the paper also touches on some other advanced 6G tech, like quantum resilient communication and using the terahertz spectrum. How do they fit into this AI slicing picture?
Well, these advanced technologies become even more powerful when they're orchestrated intelligently by AI within the network slices. So quantum resilient communication, that's about next-gen security using quantum encryption methods. Terahertz spectrum offers just massive amounts of bandwidth for those FEMMB use cases. AI acts as the brain. It decides when and how to best use these powerful but maybe resource-intensive capabilities within specific slices. It ensures the right tool is applied for the right job efficiently.
Got it. The paper also uses some specific terms like network slice instances, NSIs, and network slice subnet instances, NSSIs. Can you break those down quickly?
Sure. Think of a network slice instance, an NSI, as the complete end-to-end virtual network created for one specific service, like the whole autonomous vehicle slice.
Okay, the whole thing.
Right. Now, within that larger NSI, you have network slice subnet instances, NSSI. These are more like modular components or building blocks. They group together specific network functions and resources into manageable units within the bigger slice.
So using the car example, an NSI for autonomous driving might have several NSSIs inside it, one for sensor data, one for V2X comms, one for cloud connection.
Precisely. It allows for that modularity and flexible composition of the overall slice.
Makes sense.
And the core network itself also gets upgrades to manage this. The paper mentions the Network Slicing Admission Control Function, NSACF.
NSACF. What's its job?
It basically handles user registrations and data sessions per slice. It makes sure your device connects to the correct virtual network for the service you're using.
Okay, the gatekeeper for slices?
Kinda, yeah. And then there's the Slice Maximum Bitrate, SMBR. That acts more like a traffic cop within the slice, making sure it sticks to its allocated quality of service parameters, its bitrate limits.
Right, keeping things fair.
Exactly. And even out in the radio access network, the RAN, the part connecting to your phone or device's NAIR, are optimizations. Like Network Slice As Group.
And
Yeah, it aims to improve security and also reduce signaling overhead by managing groups of devices within the same slice more efficiently, rather than individually all the time.
It really is a deeply interconnected system from the core right out to the edge.
Absolutely. Every part needs to be slice aware.
Now, a really interesting point the researchers made was about data. They hit a critical hurdle, a lack of relevant data for training these AI models for 6G. Why was the existing data no good?
Yeah, this is really insightful. Most existing network data sets, the ones used for training AI previously, were built around 5G characteristics, or sometimes even older, like LTEA.
Okay.
And those data sets just don't reflect the drastically enhanced requirements of 6G, the ultra-low latencies we talked about, the extreme reliability, the massive bandwidths.
They're just not in the 5G data.
Not at the level 6G requires. So trying to train an AI for 6G slicing using 5G data would be like, I don't know, trying to teach a Formula One driving AI using data from city traffic.
Oh, okay, yeah. The fundamental characteristics are just too different.
Exactly.
So if the right data wasn't out there, what did they do? How did they tackle this?
They took a really forward-thinking approach. They actually created a brand new synthetic data set.
Synthetic, meaning generated.
Yes, generated specifically to represent the likely traffic characteristics of those emerging 6G services we discussed, FAMBA, ERLLC, MTC, MURLLC, and MBRLLC.
How did they generate it? What was the methodology?
They essentially simulated what the network traffic for these services would look like based on their target performance metrics and requirements published in early 6G research and standards discussions.
Okay, so what kind of parameters did they simulate? What data points are in this data set?
They focused on the key performance indicators, the KPIs, that define the quality of experience. Things like the required latency budget for a flow, the acceptable packet loss rate, which ties directly to reliability, jitter, which is the variation in packet arrival times, the necessary data transfer rates, both uplink and downlink. They also included factors like required mobility, is the device stationary or moving fast, and required connectivity density.
That makes a lot of sense. A sensor in a smart city has totally different needs than, say, someone using VR on a high-speed train.
Completely different profiles.
Yeah.
And it was clever how they handled services where the exact 6G specs aren't finalized yet.
Oh, what did they do?
Well, for some requirements, like maybe the latency budget for FMNB or MPC, which aren't as strictly defined as ERLLC yet, they use the existing 5G limits as a starting point, a reference.
Ah, okay. Like using the 5G URLC latency limit as a baseline if the 6G equivalent wasn't set in stone.
Exactly. Same approach for jitter in some cases. It's a smart way to bootstrap the process, create a realistic baseline for AI training, even while standards evolve.
And the paper mentions they use this data to train models for slice selection.
Mm-hmm.
What exactly is that process?
Slice selection is absolutely crucial. It's the process where the AI automatically figures out which virtual network is the best fit for a new incoming traffic flow or application based on its specific needs.
So the AI looks at the requirements of the traffic.
Right. It looks at those features in the data set, the packet loss tolerance, latency budget, jitter, data rate, mobility, connectivity needs. And based on those, it predicts which of those 5 main 6G service types, MBAY, ERLLC, MTC, MURLLC, or MBRLLC, that traffic best matches.
And then the network routes it to the corresponding slice.
Precisely. It steers the traffic intelligently to the slice that's designed and optimized to meet its specific QoS requirements.
That's incredibly powerful automation. And this new data set they created, is it available for others?
Yes, and this is a huge contribution. They've made it publicly available on GitHub.
Oh, fantastic.
It really is. It provides a common benchmark, a valuable tool for other researchers to develop, test, and compare their own AI-assisted 6G slicing mechanisms. It helps move the whole field forward, especially in these early stages.
That's great for collaboration. Okay, so they created this unique 6G data set. What did they actually do with it then? What AI models did they train? And the big question, how well did they actually perform?
Right, they really put it through its paces. They trained and evaluated several common yet powerful machine learning models.
Like which ones?
Let's see. Random forest, RF, decision tree, DT, XGBoost, support vector machine, SVM, and also a feed-forward neural network, FNN. A good range of techniques.
Okay, a solid lineup. And the key results, did the AI models actually manage to pick the right slice?
The results were, frankly, quite remarkable. They reported achieving accuracy of over 99% for both slice classification.
So picking the right slice type.
Exactly. And also over 99% for something called handover prediction.
Over 99%, that's almost perfect.
It's extremely high, yeah. It strongly suggests these AI approaches can be very effective at managing the complexity of these future 6G networks.
Okay, handover prediction, that sounds important too. What does that involve?
Handover prediction is about the AI figuring out ahead of time when a specific traffic flow might start experiencing poor quality on its current slice.
Like the connection is about to degrade.
Right, and proactively determining if it should be moved or handed over to a different, more suitable slice before the user actually notices a problem.
Proactive quality control, what data did they use for that?
For handover prediction, they used a different set of features, focusing more on the real-time conditions within an active network slice.
Okay, like what kind of conditions would trigger a potential handover?
The key indicators they trained the models on were things like the slice available transfer rate, or SATR basically, how much bandwidth is currently free in that slice.
Makes sense.
Also the current slice latency, SL, the slice packet loss rate, SPL, and the slice jitter, SJ. Real-time performance metrics.
And they simulated fluctuations in these.
Yeah, they used a Gaussian distribution, a statistical method, to generate realistic variations in these parameters, mimicking the dynamic, bursty nature of real-world network traffic.
So if the latency in slice A starts creeping up, or maybe the available bandwidth drops sharply, and the traffic flow in slice A needs low latency and high bandwidth, the AI could say, hey, maybe we should move this flow to slice B before it gets bad.
That's exactly the idea. Predicting the need for a handover based on degrading slice conditions relative to the flow's requirements.
Clever. Did they just use the default settings for these ML models?
No, and that's important. They performed hyperparameter tuning.
Tuning the model's internal settings.
Right, especially for models like K-nearest neighbors, KNN, and SVM, which apparently had slightly lower accuracy out of the box on this data set.
What kind of tuning?
Things like adjusting the max depth parameter for decision trees, which controls how complex the tree can get. For KNN, they experimented with the distance metric, how similarity is measured, and found that Manhattan distance actually worked better than the default Euclidean distance for this specific problem.
Interesting.
And for SVM, they tuned crucial parameters called C and gamma, which control the trade-off between model complexity and classification accuracy.
And did this tuning make a big difference?
It certainly did for SVM. They reported that after careful hyperparameter tuning, the SVM model's accuracy also shot up to over 99%, matching the others.
Wow, so tuning was key for some models.
It often is. Although, interestingly, they noted that the random forest classifier performed exceptionally well, near perfect accuracy, for both slice classification and handover prediction, even just using its default parameters.
So random forest was kind of the star performer, robust right away.
It seems like it, yes. Very robust on this data set.
Were there any interesting insights from looking at the few times the models did make mistakes, the confusion matrices you mentioned?
Absolutely. Those confusion matrices, which show what kind of errors were made, offered valuable clues.
Like what?
For instance, the decision tree model occasionally confused MURLLC with MBRLLC.
Okay, is that a bad error?
Well, technically it's an error, but the researchers pointed out it's maybe a less severe one in practice. Why? Because MBRLLC actually has more stringent requirements than BRLLC, particularly around data rate.
Ah, so putting ERLLC traffic in NBRLLC slice might be overkill, but the service probably wouldn't suffer much.
Exactly. The user experience might not degrade significantly. However, they also noted that a simpler model, naive Bayes, had more trouble predicting when a handover was needed.
And that could be bad.
That could potentially lead to service degradation or disruption if traffic isn't moved off a struggling slice in time. So that highlights the importance of choosing the right model and tuning it well.
Got it. And they also mentioned the feed-forward neural network.
Yes. The FNN also achieved over 99% accuracy after its training process completed. So multiple advanced ML techniques proved highly effective.
It's fascinating how these different AI approaches work. Now, scalability is always crucial for networks. Did they look at how these AI models cope as the network gets bigger, handles more data?
They did. They specifically evaluated the scalability of the random forest model, since it performed so well.
How did they test it?
They tested it with datasets of varying sizes, ranging from 10,000 samples up to 100,000 data samples. And they also looked at the impact of parallel processing, using multiple CPU cores or threads, what they called N jobs, on both the training time and the prediction time.
Right. Can you speed it up by throwing more computing power at it? What did they find?
Well, as you probably expect, the training time and prediction time generally increased as the dataset got larger. More data takes longer to process. However, they clearly showed a significant benefit from parallelization, especially for training. Using multiple threads, and jobs greater than one, dramatically reduced the time it took to train the random forest model.
So more processing power really helps cut down that training time, which is good for keeping models updated as networks grow.
Exactly. That's a very positive sign for scalability. Interestingly, they found prediction time was less sensitive to the number of threads.
Oh. So making predictions was fast anyway.
It was already quite fast, and adding more threads beyond a certain point gave diminishing returns in terms of speed up for prediction. They even noted some slight fluctuations or variability in prediction time when they tried using all available processor cores and jobs in the GILT1, which they thought might be due to system-specific things like how the operating system schedules tasks.
Right, complex system interactions.
But the key takeaway was that parallelization significantly helps manage training time as data scales, which is crucial.
Okay, so as we start to wrap up this deep dive, what's the really crucial takeaway message for you, our listener, from all this discussion about AI and 6G network slicing?
I think the core message is this. Artificial intelligence looks set to be the absolute key enabler for making network slicing truly intelligent, truly efficient in the 6G era. It provides that necessary adaptability, the automation, to dynamically manage network resources in a way that can actually meet the incredibly diverse and, frankly, extremely demanding requirements of all those future applications we talked about.
From immersive VR to remote surgery to autonomous cars.
All of it. AI is the brain that can potentially orchestrate it all effectively within dedicated slices.
And that novel 6G dataset the researchers created, that seems like a pretty big deal too, right?
Oh, absolutely. It's a vital contribution to the whole field. It gives everyone a much-needed, realistic foundation to build upon. As 6G standards keep evolving, having good data like this to train and evaluate AI algorithms is just going to be crucial for making AI-driven slicing a reality.
But the paper also gave a glimpse of what the researchers plan to do next. What's on their radar?
Yeah, they mentioned a few things. They want to further refine their data set, make it even more realistic, maybe add more complex traffic patterns.
Okay.
They also plan to explore techniques like transfer learning.
Transfer learning.
Yeah, that's where you might take an AI model trained on one data set, maybe existing 5G data, and adapt it more quickly and efficiently to the specifics of 6G, rather than training entirely from scratch every time.
Ah, reusing knowledge. Smart.
Exactly. And importantly, they also intend to start integrating security-related features and considerations into their future work on AI-assisted slicing.
Which is critical, of course. It sounds like this is really just the beginning for this whole area.
It really is. It's a super exciting and potentially transformative field for the future of mobile networks.
And it really leaves you thinking, doesn't it?
It does. And maybe a final thought for you, the listener. Considering this potential for AI-driven solutions to unlock such a huge range of, well, truly transformative applications and experiences in this hyperconnected 6G future. What new possibilities might this create for you? Personally, professionally, what could this enable down the road?
Some really compelling food for thought indeed. If you're keen to explore this even further, we definitely recommend checking out the original research paper and that publicly available data set. You'll find a direct link right there in our show notes. Thanks for joining us for this deep dive into the AI-powered future of mobile networks.